On Earth, gravity does most of the heavy lifting during a meal. It keeps your food pinned to the plate and ensures every sip of water travels predictably down your throat. But launch that same meal into orbit, and those rules no longer apply. Without gravity, a dining table becomes a high-stakes environment. Microgravity turns everyday ingredients into unpredictable projectiles, posing a mechanical threat to both the crew and the machinery keeping them alive. Take a look. On Earth, water pours straight down. In space, surface tension pulls liquids into a floating sphere. If that drifts into sensitive panels, a single stray drop can short-circuit a billion-dollar life support system. Beyond the immediate threat of floating liquids, there is a biological problem. Fresh food rots quickly, and early spacecraft simply couldn't carry the heavy, power-hungry refrigerators needed to keep ingredients safe for long durations. To keep crews alive for months at a time, aerospace engineers had to look past recipe development. They had to engineer the physical mechanics of a meal from the ground up. The ultimate testing ground for these dietary solutions is the International Space Station, orbiting 250 miles above the Earth. This is a standard meal on the station. It consists of vacuum-sealed pouches and dehydrated packets, designed to slot securely into a specialized metal heating tray. The lack of moisture prevents spoilage, and sealed plastic stops crumbs from escaping into the cabin. To prepare a meal, an astronaut takes one of these flat, dehydrated packets over to a designated galley station. They dock the pouch onto a nozzle that injects hot water directly into the bag. Since gravity can't stir the ingredients, the astronaut has to physically massage the pouch by hand. This forces the hot water into the dehydrated block, rehydrating the food while keeping it securely contained inside the plastic. That same containment principle applies to beverages. To neutralize the hazard of floating liquids we saw earlier, astronauts drink from foil pouches equipped with specialized straws. These feature built-in clamps to seal off the liquid the second the astronaut stops sipping. Even with these tools, mealtime requires incredible discipline. Astronauts eat with slow, deliberate movements, cutting food carefully to ensure no stray droplets break surface tension and drift away. This engineered approach guarantees that a crew gets enough calories to survive a 6-month mission. However, physical survival is only half the battle. The human mind requires sensory stimulation to endure total isolation. After a few months of squeezing brown paste out of silver foil, astronauts frequently experience menu fatigue. They lose their appetite, and the repetitive, sterile nature of the diet begins to take a noticeable psychological toll. Relief comes from uncrewed cargo ships. When a robotic arm grapples a resupply capsule and docks it to the station, it brings something highly anticipated. Tucked inside the cargo hold is a small allocation of fresh produce, things like crisp apples, crunchy raw carrots, and bright fresh oranges. The value of this fruit isn't merely nutritional. It lies in the loud, satisfying crunch of a fresh apple and the sharp, citrus spray of an orange peel. Those are vibrant sensory experiences impossible to replicate in a freeze-dried packet. Space agencies schedule these deliveries as engineered morale boosters. A fresh piece of fruit serves as a sensory umbilical cord, briefly reconnecting the crew back to life on Earth. This diagram illustrates the next logistical hurdle in aerospace engineering. The International Space Station orbits just a few hundred miles away, but multi-year missions to Mars will stretch our supply chains across millions of miles of empty space. At that distance, calling for a cargo ship full of fresh apples is physically impossible. The umbilical cord to Earth is severed completely. To survive deep space, humanity must change its approach to food. We can no longer rely on storing rations for the journey. We have to build systems that autonomously create calories in transit. That agricultural testing is happening right now. Up on the ISS, astronauts are running active experiments inside onboard cultivation chambers, observing how plants grow in a microgravity environment. This time-lapse shows red romaine lettuce unfurling under the glow of specialized LED lights. Crews carefully tend to these hydroponic gardens, watering the roots through customized zero-G syringes until the leaves are ready to harvest and eat directly on the station. This method of orbital agriculture functions as a closed-loop life support system. It provides renewable nutrition while simultaneously delivering the psychological comfort of tending to a living, growing plant. Evolving the space diet from a rehydrated pouch to a fresh leaf of hydroponic lettuce secures a self-sustaining food source for a crew. It also provides the biological framework humanity needs to survive on other planets.